Okay. All right. Hope everybody had a nice break and all energized. No. Never. Okay. Well, anyway, let's energized or not, let's get you energized for the analysis. A little bit more excitement, please. Okay. So this is where we stopped last time. We're going to finish titrate acidity today and move on to fat characterization. So you all did the lab, obviously, and then you'll be submitting your lab report on Wednesday, right? So you'll be doing these calculations, and let's do some derivation of this equation. So which you see quite a bit, and you also saw, some of you in lab today saw that we use this kind of equation to calculate different measures for fat characterization. So how do we come up with N by V times equivalent weight times 100 over weight times 1,000? How, if you understand how we come up with that, then you will remember the equation, because you need to remember that equation. Okay, so in titratable acidity, what you did is you had your beverage, you added phenolphthalein, and you were titrating the acid with a base. At equilibrium, you get the last drop that turns pink. That means milli-equivalent of acid equals milli-equivalent of base at neutralization, right? And that's our essence, our beginning. So milli-equivalent equal milli-equivalent. Okay. That was weird. That's a cue, my dears. Here. Okay, so that's acid, base. So with that, normality times volume equal normality times volume, right? Again, this is for base, and this is for acid. So we are after the percent acidity, right? But we do have the normality and volume of the titration of the base. So these values we have. We have the volume of the acid. We don't have the normality. Okay. Normality happens to be also equal number of equivalents times molarity times volume equal N by V. Again, here we're still base, and this is acid. Okay? We're all following? Normality equal number of equivalents times molarity. Number of equivalents for acid is the number of hydrogens that that acid can donate. So if you have one carboxyl group, number of equivalents is 1. If you have 2 carboxyl groups, number of equivalents is 2, 3, 3, and so on. Okay, so number of equivalents times molarity times volume. Okay, molarity is number of moles over volume, right? We're all following? No, not volume. What? Number of moles. Oh yeah, minus volume, of course. Why am I? Okay. So I'm just going through all of this. This stays the same. Volume here and volume here will cancel. Now, number of moles equals mass over molecular weight. Okay? Number of equivalents all right. So I'm after mass of the acid, right? Because I want to get percentage of the acid. So I need to know that. Okay. So I'm solving for mass. So then N by V times molecular weight over number of equivalents equals mass. Are we all following? If you get stuck anywhere, stop me and I will repeat. Yes, Lauren, where did you get?
The number of equivalents divided the whole thing, or just the...
This is, I want it specifically over this because this becomes your equivalent weight, right? So again, if you have acetic acid, molecular weight will be equal equivalent weight because acetic acid has one carboxyl group. But in the case of citric acid, like you did in the lab, you would divide the molecular weight of citric acid by 3. You will get the equivalent weight of citric acid.
So is that like a special way how to do like number of equivalents of like the line and the O?
Oh, well, some people do number like that. I mean, number of equivalents. It's not a special way, it's my way.
Okay.
It's a designation for a number. You never seen this? The number? Well, how do you do it? This? Hashtag. Okay. Hashtag equivalent. Okay. Back to that. And then to do percentage, then it will be this divided by the weight of the sample times 100. Then you will get percent titratable acidity. So there you go. Oh, one thing I didn't add is your volume is in milliliter, but normality is per liter, so we correct and you divide by 1,000. So hence this equation. N by V of the base, equivalent weight of your acid, whatever is the main acid in your beverage, whatever you are determining, lactic acid, acetic acid, citric acid, malic acid, whatever it is, you would divide its actual molecular weight by the number of equivalents based on how many hydrogens it donates. You divide by the weight, multiply by 100, divide by 1,000 to correct milliliter to liter. Okay, so if you want, take a picture of that so you understand how we derived this equation. And if you understand this, then you will remember your equation. Okay, it's simple, basic chemistry of equivalence. Okay, so let's do that. That was supposed to be part of last sheet. I don't know if you turned it in already. Yeah. You did? Yeah. That's okay. Just do it for practice. Just apply the equation. And I showed you citric acid here. It has 1, 2, 3 carboxyl groups. So hashtag equivalence is what? 3. I have to be current, my sin. How many bottles of water do you have back there? Okay, anybody with a number? Okay, Lucy? We rounded up to 0.6, and yes. So basically, you just apply the equation. So normality times the volume. 64 comes from 192 divided by 3. That's your equivalence weight. And then divided by the 15, which is the milliliter of the sample. We correct for milliliters to liters, multiply by 100. That would be 0.6%. Weight by volume in this case, okay? Because we have the volume of the sample rather than the weight of the sample, so it is weight by volume percent. Okay, so mind you, acidity, concentration of acidity is always low. So if I ever ask you to make up your own data, which I like that a lot, remember that titratable acidity range is really low. You won't get 10% or 20% in the different fruits, for example. And this is a table I believe is in your book chapter. This is just FYI so that you know and have an idea of the range of titratable acidity so that you see it's not usually high. Like we mentioned several times, titratable acidity is always measured based on the predominant acid. That doesn't mean you don't have any other acids in your sample, but we always take the predominant acid, use the molecular weight of that predominant acid in the calculation. We also use that to determine Brix over acid ratio, which is an indicator of acid flavor and maturity. And then it's also used to determine volatile acidity. So if you want to determine the quality of wine, you want the wine do not have a lot of acetic acid in it. It would taste vinegary, right? So you would determine, you would measure the titratable acidity of wine as such, and then you boil the wine a little bit to evaporate acetic acid because it's volatile. And then you do titratable acidity again. The difference would be the amount of acetic acid you had in your wine. And you don't want a really high amount of acetic acid in your wine. Okay, well, that concludes pH and titratable acidity. Finally, we can move on to fat characterization. Only if I can find my arrow. No, I don't want to show you my email. Why did that happen? Okay. So fat characterization, there are so many tests that are involved in characterizing fat, and we're going to talk about several of them today. So which of the following is true? I see many hands up. I'm going to go with Ali. Huh? C? Okay. Anybody else? Walter? I'm going to play the game. All right, Oaf. It's A and C. Sarah?
B and C.
B and C, wonderful. What? Molly?
I was going to say all the above. Oh, no. Just kidding.
Ali was right. It's just C. What? It's not a measure to detect advanced stages of, it's the primary stage of oxidation. Peroxide is the first oxidation product. It will move on to secondary oxidation products. Measuring of hexane, oh, did I say just C? Oh, I lied. It's B and C. What? I thought this says primary. I should change it for next year. No, hexanal is a secondary oxidation product. So peroxide moves into hexanal, pentanal, malonyl aldehyde. So if you find hexanal, that means you have an advanced stage of oxidation. Yes, Sam.
If you give the entire peroxide curve at different periods of time and you measure the whole thing, does it then count for like the late stages of oxidation that you can tell from that curve?
Well, you are ahead of the game, Sam. I want to hold off because you did the lab, others didn't yet. So I will get to that as I progress in lecture. So I don't want to be ahead of myself. But yes, I know what you mean. And the answer to your question is no, but wait until I get to that point. All right. So B and C, I mean, Ali was 50% right. Okay. All right. Saponification value is often measured to detect level of fatty acid saturation. Ketone. It is false because it is the iodine value. Saponification value has a different role or different characteristics, measure different characteristics. So we'll talk about that later. Okay. When we say fat characterization, what do we mean and why is it important? Give an example of a fat characterization test and why is it important. What does it mean, fat characterization? What are we characterizing? The age of fat? The type of fat. Why is that important? It's very important, but why is it important? Why is it important? Are you going to answer that question?
Yeah.
Okay, Stephanie. Yes, so fat characterization, okay, so there are two things going on. The type of fat is important because authentication, right? So different fats have different refractive index, for example, saponification value, so you can detect adulteration. But what Stephanie said is also important because on the nutrition label, we look at the different fats as well. Saturated, polyunsaturated or just unsaturated, trans fat, cholesterol. So these are all components of the fat, so we need to know these. This is one category. Identifying the different types of fat is another form of fat characterization. Good. So we talked about authentication, fat characterization. Tiffany?
Like functionality.
Such as? What?
Like I feel like just, I don't know, like being in a liquid state versus like a solid state.
Yes, so solid to liquid index, for example, solid fat to liquid, solid fat index. Is it right? Is that how you say it? Solid to liquid fat index. Okay, so that has to do with the consistency and spreadability of the fat. The lower the melting point is, the better the fat is spreadable. And the more unsaturated you have fatty acid, the lower is the melting point, the more spreadability. That's why sometimes in a butter-like product, they have oleic acid in there to make it more spreadable. Monique? Oxidation, yes. Very good. So shelf life stability. So we look at oxidative rancidity, looking at primary oxidative products, secondary oxidative products.
The amount of free fatty acids can indicate the level of refinement.
Oh, wonderful. So the level of free fatty acid, and we'll talk about that when I show the processing scheme of oil. So yes, so when you press the oil, you get crude oil. And this crude oil has free fatty acid. So the virgin oil, for example, olive oil, that's not refined, so it has higher free fatty acid than a refined oil. In refinement of oil, does anybody know how they refine oil? Do you cover this anywhere in the in food camp? So how do you refine oil? Huh? That's hydrogenation. Yeah? You?
You do like degumming and then deodorization, like many different steps.
There's the degumming is a different step, deodorization is a different step. treating with NaOH. You treat with NaOH, and the NaOH reacts with free fatty acid, gives you soap and water, and the oil is centrifuged, and the soap and water is on the top, is separated from the refined oil. So it's a measure of refinement. If you have high free fatty acid at the beginning when you obtain an oil, or after you refine the oil, you test to see if the refinement went well. Sam?
Doesn't it indicate carcinogens?
That's when you get to oxidation and advanced stages of oxidation. You get the malonylaldehyde, the cholesterol oxide, mutagens. Yes. So that's bad for our health. So that's another thing. I was going to say rancidity, hydrolytic rancidity. So we do have oxidative rancidity, and we also have hydrolytic rancidity, which could be due to presence of lipases. Or say you're frying your potatoes in oil, and the potatoes have water in them, and then water, oil, heat, you're breaking the triglycerides, and you're having free fatty acid. So it is an indication of the age of the oil and how many times can you still use that oil to fry. So these are all examples of, and here they are. So nutrition label, we talked about having total fat, saturated, trans fat, cholesterol. So, and how can we get trans fat in our oils? What process may result in trans fat? Yes. Sarah, you said that, yeah? Not Sarah, Sophia. Okay, yes, hydrogenation. So processing, that would be a processing effect. So when you have incomplete hydrogenation, some of the cis formation of your double bond can become trans, and that trans has cardiovascular impact, so it has health impacts. We talked about palatability, that has to do with the solid fat index, and then the spreadability of the butter, how fast it melts in your mouth. And safety, we talked about oxidation products that could happen due to oxidation. And shelf life stability can be both oxidative and hydrolytic rancidity. So here are more of what we said in terms of the different types of fats, the shelf life, and also measurements of presence of similar ingredients similar to fat, like the olestra. It doesn't have caloric value. It is basically fatty acid 608 linked to sucrose, undigestible, give you the feel of fat. And also fat with short and medium chain triglycerides, they don't usually contribute to the 9 calories per gram. So understanding how many of those we have by doing fat analysis characterization, that will indicate the contribution to calories. Here's the oil processing, a schematic of that. So, so there's a process where you go through from the seeds, and then metal, dehulling, shelling, crushing, getting the oil, doing the refining here with alkali, water and alkali washes to get out the free fatty acid, and then bleaching and deodorizing. Then you can do hydrogenation of the oil if that's what you're after as well. So different steps. So we measure iodine value, for example, before and after hydrogenation, because iodine value is an indication of unsaturation. With hydrogenation, you want to break the unsaturated bond and make it all hydrogen, give it more hydrogen, and then you measure the degree of unsaturation afterwards to determine if hydrogenation was complete, for example. We talked about deep frying and the presence of free fatty acids. And when you have higher fatty acids in your oil, you have faster oxidation. Because free fatty acids are more prone to oxidation than fatty acid linked to glycerol. Okay? Do you know what winterizing is? Have you heard that term before? What does it do? Okay, Sarah.
Make the layer less cloudy of certain oils, like when you separate them out.
Yeah. So basically, winterizing, from its name, is you bring the temperature of the oil down, you cool it down, and then any solid material would crystallize and precipitate, and then you separate the crystalline material from the oil. Then the oil you can use in salad dressing, put it in the fridge, and it won't cloud. So that's the process of winterizing, chilling the oil to remove crystals so that the oil remains clear during refrigeration in applications such as salad dressing. And we talked about melanaldehyde, which are products of oxidation, and cholesterol oxide, which are mutagens, both of them. Okay. So there are different fat characterization methods. There are certain methods that you would do specifically on a bulk fat or oil, like you're doing in the lab. Those of you on Monday did different types of oils. So we do on coconut oil, lard, olive oil, corn oil, etc. We do a bunch of characterization tests. And then there are methods for lipid oxidation specifically, and then methods for lipid fractions to know the components of the different lipids. So we'll start off with the bulk characterization. So if we want to characterize oxidation, let's say in a product that is high in fat, but it is not pure fat, we extract the fat first. So if I want to monitor, not necessarily high in fat, if I want to monitor lipid oxidation in grains, for example, which we do quite a bit in our lab, so we extract the oil first, and then we determine the oxidation of this oil that we extracted. So we extract with different solvents. There are usually hexane isopropanol or coliform methanol combinations, and then we evaporate the solvent, we get the oil, and we characterize that oil from the original sample. But while we prepare the oil, it's very important to minimize heat, oxygen, and light exposure, especially if we're after determining oxidation. So you don't want to expose your sample to any alteration. Physical characteristics, there is a whole section in your book, so you can read that to get more detail, but I'll go over them pretty quickly. So refractive index, it's an indication of saturation of the oil, and it's often used as a quick identification of your oil. A melting point, every oil has a different melting point, and same for every oil has a different smoke, flash, and fire point. And I have a story for the smoke, flash, and fire point. Yes, indeed. I almost burnt my house down with that smoke, flash, and fire point. So, do you want to hear the story? Yeah. Okay, let's hear the story. So, I wanted to boil eggs, but on the stove I had the eggs and water, and I had another pot with oil, because I deep fry a lot of stuff. I turned the stove on and went down to do some work. Later on, I hear the alarm, fire alarm, come up, my oil is on fire, because I turned on the wrong knob. My daughter was in the room. You know, if you are a smart mother, you'll tell your child to leave the house. Stay in the room, that's what I said. And then I took the pot with oil and fire. What do you think I did with it? I opened the tap of water, and then an explosion happened. In my face, the top of the ceiling all blackened out, and the thing still going on fire. Luckily, to the story, there was snow outside. So I opened the door and I throw the pot on the snow, and then what happens? Another explosion. The neighbors thought I was crazy. But yeah, that's the story. So you don't want to get your oil to burn. That's, I didn't make the eggs at the end of the day. I was so nervous and I was burnt. And I had burn on my hands and I had to paint the entire kitchen. But we survived. And then my daughter said, you almost killed me. And I said, yes. So, but we survived. Anyway, you cannot fry with olive oil, for example. You can fry with corn oil. Olive oil has low smoke point, flash, and fire point. So the temperature at which it starts smoking, and then you get a spark, and then you get fire after that. So olive oil is not for frying, it's used for salads, whereas corn oil is used for frying. So that has to do with how much oleic acid you have compared to linoleic acid, for example. So linoleic acid will have higher smoke, flash, and fire point. Okay, so the cold test and the cloud test, they're both can be used for checking the winterization process. Okay, so cold test is you actually chill it to the same temperature you would when you're winterizing the oil during processing, and to see if you get crystals. If you get crystals formation and sedimentation, it means the winterization was not done adequately. The cloud test is similar, but instead of chilling it to lower temperature, you chill it to a certain amount, a certain temperature, but then you measure cloudiness, and you actually measure cloudiness by an instrument to measure cloud formation, which the cloud formation is the initial stage before crystallization. So the oil starts to become cloudy, and if you cool it a little longer, the cloudiness will sediment into crystal solids. The solid fat index is an indication of degree of saturation versus unsaturation. So the higher the degree of saturation, the higher is the solid fat index. And in the book, it explains the method of determining that. And then consistency and spreadability, you do that by texture analyzer equipment to determine the consistency of the solid fat, if you have a butter or margarine, and then the spreadability as well of that, because it's very important characteristics. So these are the physical characteristics. Moving on to actual wet chemistry characterization of fat, and starting off with the iodine value. So it's a measure of the degree of unsaturation. So if I tell you define iodine value, you would tell me it's a measure of a degree of unsaturation, and it's very important that you finish that. It's not just a matter of measure of degree of unsaturation. You want to define it as the grams of iodine absorbed by 100 grams of sample. This you need to know. That's basically the unit of the iodine value. Grams of iodine absorbed by 100 grams of sample. So what some of you did in the lab already is you got your sample, fat sample, and you reacted with excess iodine chloride. Then you break the double bond, and you get remaining, because not all of the iodine chloride will be picked up by the double bond. So you will have remaining iodine chloride. And then you react the iodine chloride with potassium iodide, you get iodine. And then the iodine, you add starch. Okay, so it's not purple, blue, it's more like purple color. And then this is the indicator, iodine and starch. You'll get purple, blue colorish color. And then you titrate with sodium thiosulfate. And then you titrate to colorless. And then you use this nice derivation to get to here. You are going after grams per 100 grams. So in this case, it's blank minus sample. Why? Because in blank, you don't have anything here. So all of what you added is going to remain. And you will get the maximum amount of iodine when you don't have any double bonds, nothing in the sample. Okay? But if you have unsaturated fat in there, that some of that will react here and you'll have less. So your sample will always be less than the blank. Okay? So it's blank minus sample times the normality of sodium thiosulfate. 126.9 is the molecular weight of iodine. Divided by the weight of the sample, you're correcting milliliter to liter, you divide by 1,000, you multiply by 100 because it is per 100 grams of sample. So that's how the equation came. So it's the same concept here. You apply it here, and you get the iodine value, which is grams in 100 grams of sample. So we use it for fat characterization or fat identification because every oil will have their own iodine value because of the unique amount of unsaturation. Following hydrogenation to determine if you had complete hydrogenation of your oil. And picture this, it's also a measure of oxidation because double bonds are broken when you form peroxide, right? So today in the lab we had an example. One of the oils had started with really high peroxide value, and their iodine value was low. So that means there has been oxidation, even though it was supposed to be fresh, oxidized oil with iodine value reduced. Okay. Next is saponification value. So again, if I say define it, it's an index for average molecular weight of triglyceride in your sample. So, and again, remember the unit. It is defined as the milligram of KOH required to saponify 1 gram of sample. So it is milligrams of KOH, which it's a base that saponifies the triglycerides, so it breaks off the glycerol and give you potassium salts of fatty acids. So how many milligrams of KOH were taken by 1 gram of fat is the saponification value. So it's an easy process. So you saponify with KOH and then with excess KOH, and then you run a blank. If you have a blank, there won't be any triglycerides here. All of your KOH, you will have to titrate with HCl. So again, the blank is greater than your sample. So you put phenolphthalein with base will give you the pink color. So again, here the titration is to clear. So you're titrating with HCl to clear. The saponification value, because it is milligrams per gram, notice there is no 1,000 here. You do not divide by 1,000 because it's in milligram. So you do not have to convert milliliter to liter. You keep it in milligrams. And then the other thing you notice, there is no multiplication by 100 because it is per 1 gram of sample. So you only divide by the weight of the sample to get milligrams of KOH per 1 gram of sample. 56.1 is the molecular weight of KOH. Okay? And this would be the volume for HCl, and this would be the normality for HCl. Okay? Now, we said here it's an index for average molecular weight of triglycerides in the sample. So if you get saponification value, you can calculate molecular weight. How? Here's an example. Give it a go and turn it in for +2. So I have this up for a reason, and I have that for a reason. You need these equations to get you started. So what's the given? What's the given? The saponification value is 190 milligrams of KOH per 1 gram of triglycerides. That's the given. First thing I want to do is what with these numbers? Do I have equal units? So first thing I want to do is I want to convert this to grams. Then what? I have 3 moles to 1 mole. One mole will have how much molecular weight? Molecular weight of KOH is 56.1. I'm after calculating molecular weight, right? So 3 moles will have 3 times 56.1 grams in molecular weight, right? And here, I want to solve for the molecular weight of triglycerides. So what would the equation be? Solving for x, right? So I have 0.190 grams will saponify 1 gram. This much will react with how many? How much? 3 moles to 1 mole. So what would be my equation? You get that? You're all following here? Okay, so what would be that value? So I'm solving for the molecular weight of this one. So 1 mole of this, what's the molecular weight of 1 mole? When the molecular weight of 3 moles is this, and when I know that 0.19 grams reacts with 1 gram. So what is that value? 80 what?
885.8 grams.
Okay. So that's the molecular weight of the triglycerides. I want the average molecular weight of the fatty acids. How do I solve that? I use this equation, right? So the triglycerides plus 3, sorry, I forgot to add that, plus 3H2O will give me glycerol plus 3 fatty acid. I forgot to give you the glycerol molecular weight, which is 92. Okay. So now I calculated 885.8 plus 3 times 18. 3 times 18, is it 54? No, 54. Glycerol 92 plus 3 fatty acids. Bring 92 over. What would be the final number? This plus 54 minus 92. Equal 3 fatty acids. The one fatty acid I would divide by 3. which happens to be the molecular weight of oleic acid. So the saponification value of olive oil helped me calculate the average molecular weight of the main fatty acid, which happens to be olive oil. Okay, so if the saponification value was less than 190, it's definitely an adulterated oil. Okay, but would it have been adulterated with an oil that has higher molecular weight fatty acid or lower molecular weight fatty acid? Think about that. If it was less, would you have higher or lower? It's higher. Would you like to explain why? Yes, okay, that's the simple way of thinking about that. But a large molecular weight will require less amount of KOH to saponify it. Okay? You will have less mass in 1 mole when you have larger molecular weight. So if you have less mass in 1 mole, then you need less KOH to saponify it. Okay? So it's the opposite direction. But again, if you want to simplify matters with Monique, what's in the denominator? Higher value, lower number. Okay, I really like this, so make sure you know how to solve this. You can take a picture of that, or this, because it has much more detail.